gravity is not always at 9.81. When you move further and further away from the surface of the Earth, the gravitational field strength value will start to decrease. All right, so when you're near the surface of the Earth, yes, the gravitational field strength is rather strong, but when you're further away, it does get weaker and weaker and weaker. All right, so this is the true life diagram of what the gravitational field length should look like, but when you're near the surface of the Earth, they more or less appear to be parallel to each other. A good way to demonstrate the gravitational field lines is by taking any given object and just dropping it, and rinsing, repeating in different parts. And if you reverse back into the recording, you'll see that the lines are more or less parallel to each other. All right, so near the surface of the Earth, we can assume that the gravitational field strength will be uniform and consistent at 9.81 newtons per kilogram. When we move further away, the value does decrease. There's also another factor that will affect our gravitational field strength. So it's not limited by our distance away from the center of the Earth. Another factor is what is directly underneath us. All right, because if we're standing on top of, let's say, a whole pit full of gold, we'll notice it will feel slightly heavier, and that's because there's more mass underneath us. If you recall from back in grade 11, our weight or force of gravitational attraction is equal to capital G, mass of the big planet, mass of the small object, all over r squared. All right, so if there's more mass directly underneath you, you will feel slightly heavier. All right, so whenever you decide to measure, for example, a kilogram of gold, you do have to calibrate it each time when you're in a different city, all right, because the gravitational field strength is not always at 9.81. All right, so knowing that the gravitational field strength will decrease as we move further and further away from the surface of the Earth, well, one thing to recall is that by definition, work is equal to force applied times distance. And it's assuming that the force applied is a constant value. All right, but when you move further away from the surface of the Earth, the force of attraction between you and the Earth does get less and less. So it takes a whole lot more work to lift an object from here to here than it does if you're really far away from the surface of the Earth and you move it the same exact delta or the same exact distance. It's a whole lot less. All right, so the area underneath this graph defines the amount of work that you've done. So the further away you are from the surface of the Earth, the less work that's required towards moving it. Okay, however, that leaves this area as a big fat question. Now, if you take a look at the curve that we have over here, yes, that is a 1 over x squared correlation. All right, so it's an inverse squared correlation, meaning that, yes, you'll create a vertical asymptote and that will approach infinity, but that won't be the case when we're at the center of the Earth. You got to keep in mind that the Earth is not just a dot that we're so far away from, roughly around 6,000 meters or about, 6,000 kilometers. Okay, there's a U. There you go. Okay, so the Earth is not concentrated, 6,000 kilometers away from the center of the Earth. Instead, the Earth does take up a rather large amount of volume. Okay, so as we go towards the center of the Earth, you got to keep in mind that there's this mass that's being pulled to you, from the surface of the Earth, as well as that from the core of the Earth and on the other side. So theoretically speaking, if you are able to make it to the exact center of the Earth, since you're being pulled in all directions, you will technically start to feel weightless. And this was emphasized in a movie which I can't play for you, unfortunately, but the movie is called Total Recall. And if you recall, somewhere in the movie, they're in this space elevator where they pass through the center of the Earth and then they start inverting because there's no more weight towards the center of the Earth. All right, so that's a cool movie reference to this. All right, but from a practical standpoint, we're not going to deal with anything inside the Earth. All right, we're going to start from R1, which we'll call RE from now on. All right, from the radius of the Earth. Okay, so to be able to do today's calculations, you do need to know a bit of calculus. And I went through this back in, I believe, lesson 2.02, so you can rewind back there to listen to it in its entire. Here, I'm just going to summarize everything one more time. All right, calculus, by definition, is finding the slope of a tangent. All right, so if you're given any given curve and you want to find out what the slope of the tangent is, you can apply calculus in figuring it out. All right, and through calculus, it'll give you a mathematical function that which then you can do a calculation afterwards to figure out what the slope of it is. for example, let's say this curve that I have over here is described by y is equal to x squared. And if you sat down and you pulled back your grade 11 tangent exercises that you've gone through in physics class, you'll know that right at x is equal to 0, the slope is equal to 0. And if you measure the slope at x is equal to 1, the slope over here will actually measure a slope of 2, believe it or not. And at x at 2, if you measure another tangent over here, this will have a slope that will be at a value of 4. And if you measure at 3, the slope of here will have a value of 6. In other words, you'll have a graph that looks like what we have over here. Okay, so at 1, 2, at 2, we'll go all the way up to 4, so on and so forth. In other words, if you were to describe this as a mathematical equation, the function for this, I'll just call it f of x, why not, is equal to 2x. All right, so if this original f of x is equal to x squared, then the slope of it, which often we just use apostrophe to mean the derivative, is equal to 2x. Okay, and there are a bunch of mathematicians and scientists that notice that there's a pattern here. All right, and to go from this mathematical function to this mathematical function, well, there's this thing called a chain rule where all you have to do is take the exponent, bring it down, and multiply it by the coefficient. All right, so since x squared really has the number 1 over here, you multiply 2 by 1, and that will give you the 2. You then take the exponent and you subtract 1 from it. So 2 subtract 1 will give you 1. Of course, no one really writes 2x to the power of 1. You'll just simply call it 2x. All right, and that's how you quickly find a derivative. And we can continue this exercise from here all the way over here. All right, so if you treat this as a velocity time graph, and this first one was a position time graph, now the third one will be an acceleration versus time graph. Should do it that way. Yeah, that'll make more sense. Acceleration versus time graph. Okay, which will take the slope of this, and I think that's fairly straightforward. If you know that the function is 2x, the slope really is just the number 2, right? So the answer for that is equal to 2. Okay, but you can also apply calculus in solving this as well. You have a function which is 2x or 2x to the power of 1. You bring the 1 down, 2 times 1 gives you 2. 1 subtract 1 gives you 0, so it's 2x to the power of 0. And any value that's non-zero to the power of 0 will give you the answer of 1. So that will just disappear, and that's how you quickly get the derivative. Now, we don't really need to worry about derivative in today's lesson. We actually need to know about the antiderivative, all right, or the integral. All it is at the end of the day is finding out the area underneath the graph. And the area underneath the graph can also always be solved by the previous function. All right, so that's all an integral is. All right, you're finding out the area underneath the graph using the previous function. So you're pretty much just going backwards in time when you're solving for the integral. All right, so if you do the integral of 2, which this is how you write it out, then you'll have an answer of y apostrophe is equal to, well, what was 2 before it was the derivative, right? And it would have been 2x, right? So the antiderivative of 2 is 2x. Done. And what is the antiderivative of 2x itself? Well, then you go back in time, and you know that the x probably had a 2 on top, all right? And this 2 here, well, probably went upstairs, so it would have been x squared. So the derivative of x squared is 2x. Okay. So that's all this squiggly line is. The squiggly line means, well, before you did the derivative, or the antiderivative. All right, and we need to know that because, again, the antiderivative always tells us the area. All right, if you recall from back in grade 11, the area underneath the VT graph will give you your position. All right, it'll give you the function for the position time graph. Okay, now, finding out the areas of, for example, a rectangle is nice and clean, right? You just simply multiply the base by the height, and that's fairly easy to solve. However, in a lesson like today's lesson, well, we have something that looks more like this, all right? Why do we have something that looks like this? It's because we have to use a function that looks like this. Fg is equal to gm over r squared. All right, if you plot it out, the curve would look like this. And if you're trying to find the work underneath a force distance graph, well, then you have to find out the area underneath this crazy looking squiggle here, right, which is not very clean at all. Okay, so let's go and try to find out the mathematical function that describes the area underneath the curve. All right. So in this case over here, let's just say that we have a curve that is an inverse square correlation. And you can see why we're going to do that exercise right now, right? Because it's directly related to today's lesson. Okay, so we have a function that which looks like 1 over x squared. What is the antiderivative of that? I guess before we move forwards, let's just do a little bit of practice. Okay, if we know that y, let's say we have an example that y is equal to x cubed. Okay, and we want to find out the derivative of it. Well, we simply bring the 3 down, so we get 3x, and 3 minus 1 gives you 2. All right, so the derivative of x cubed is 3x squared. And if you decide to do the derivative of this, then you'd bring the 2 down, and 3 times 2 is 6. 2 minus 1 is 1. So the second derivative of this function over here would be equal to 6x. And if you decide to do the third derivative because you're bored out of your mind, then yeah, the answer is just 6. Okay, and these are examples where you'll notice that the exponent is a positive value, but in this case over here, it's a negative value. In fact, before I move forward, let me just explain what I did right over here. Okay, first off, I want to evaluate and find out the area underneath this curve relative to x. That's why I call it dx. Normally you'd write the normal letter d. I use die, and that's just so that in case if you see the letter d afterwards, you don't confuse them between d and the derivative of. Okay, so that's why I'm intentionally using that. Now this function over here can also be rewritten as x to the negative 2. Right? Remember that anytime that you have a negative exponent, it just simply is asking you to find the reciprocal of it. Okay, and that's why we want to go to the exercise of how do you deal with negative exponents. Okay, and we'll do the derivative first, and then we'll think about the antiderivative afterwards. So let's say I give you a function which is 5x to the power of negative 2. What is the first derivative? Did you say negative 10x to the negative 3? Good. And let's say we decide to do the second derivative of this. All right, so the derivative of negative 10x cubed. What does it give you? Or x to the negative 3. Yeah, negative 3. What does it give you? All right, you bring the negative 3 down, so double the negative becomes positive. So you get positive 30x to the power of negative 4. And yeah, you can try it again if you really want to. Okay, so again, as you're going down, you're doing the derivative. But as you go up, you're doing the antiderivative, also known as the integral. And that's what we want to do over here. We want to find out the integral, or the antiderivative, of x to the negative 2. All right, so you'll see that if you had negative 120 to x to the 5, the antiderivative would have looked like that. All right, and this part over here requires a lot of mental thinking in solving the problem. Okay, so we know that to get to negative 2, it probably was a negative 1 originally. Okay, but that negative 1 had to be brought down before it became negative 2. Okay, so if you were to do the derivative of x to the negative 1, then you'd end up getting negative x to the negative 2. All right, but we'll notice that here we didn't have a negative sign over here. So that means that x to the negative 1 was not the original antiderivative. Instead, if you thought about it, it should have been negative x to the negative 1. Because if you do the derivative of negative x to the negative 1, then you'll get the negative 1 brought down, which double negative becomes positive. So you get positive x to the negative 2. Okay, so the antiderivative of x to the negative 2 should have been negative x to the negative 1. Okay, so now we have the function that can be used to calculate out the area underneath here. Okay, so yeah, let's compare and contrast between what we did in grade 11 versus what we have to do in grade 12 now. In grade 11, we kept things simple. We just simply said that the work, by definition, is the area underneath the force-distance graph. And since it looked like a nice, pretty rectangle, then, rectangles are base times height, so force times distance. And that was our definition of work back in grade 11. Okay, but let's take this from a calculus perspective now. All right, work is the integral of the force function relative to distance. Okay, now the value of f is a constant value. All right, so it's just constant. It could be any number, but it's just a fixed value, and we'll just describe it by the letter f. So what is the antiderivative of a constant? All right, Well, it's just simply equal to f times the variable, which is d. All right, because if you try to do the derivative of this, well, then the d to the 1, when that is brought down, then you simply get 1f, and then 1 minus 1 gives you 0. So f times d to the 0, which is equal to f. Okay, so we know that the integral is f to the d. Okay, so the antiderivative of f is f times d. Done. Okay, so that's the proper way to do these calculations, not the lazy way of base times height. That's just what we do in grade 11. Okay, because in grade 12, sometimes we have things that are not so pretty, that look like this. All right, and as I mentioned, the reason why this curve looks like this is because Newton noticed that the relationship between the force of attraction between two objects is based upon a constant times the mass, or the product of the masses of the two objects, divided by the distance of separation squared. Right. So if we need to find out the area underneath here, then we need to do the integral of that crazy looking function. Okay, work is the area underneath this crazy looking function. So what is the answer? Okay, before we move forwards, we know that g is 6.67 times 10 to the negative 11. All right, it's a constant. The mass of the big planet is constant. The mass of the satellite or the little object, it's constant. So because they're constant values, they don't really have to be described inside the integral. In fact, it could be moved outside like this. So really all we need to pay attention to is just this part over here. And if you recall from what we learned, the integral of 1 over r squared is equal to negative r negative 1. So we could just multiply that by GMM and get to our answer. Now r to the negative 1 has the same meaning as negative r downstairs. All right, so the work required to do this is equal to GMM over negative r, but just to be grammatically correct, the minus sign should always be in the numerator, not in the denominator. And that's why the final answer is just that. Done. Okay. Now, with regards to integrals, we don't normally write them out as a general expression. Instead, it was very specific because we want to find out the integral between two different points, right? For example, we want to find out the area from here to here. All right, how much work have you done up to this point over here? Let's say it's at 3 meters away. All right, and how much work have you done at, I don't know, 10 meters away? Well, then that will be a greater amount of area. All right, so we usually end up placing numbers in the integral over here to tell the reader that, you know, I only want to evaluate only at a certain space here. So let's say that we only want to evaluate the work done between 3 meters and 10 meters. Then at the bottom, we'd write down 3, and at the top, we write down 10. Okay, because we're only concerned about the work that's done from the 3 meter point to the 10 meter point, and we don't care about anything else there. Well, anytime that you write it down in an evaluative form, usually when you do the integral, you'd write out a vertical line to tell the reader, hey, I'm not done yet. I'm trying to evaluate between these 2 points here. I want to find out the differences between these two, okay, between the 3 and the 10. And when you write it out like this, what you're telling the reader is that you want to sub in the 10 and the 3 into the variable d, but you want to find out the difference between the two. So you can take the function, and then it's going to be f times, you know, the 10 meter mark minus the value of f, whatever that force is, at the 3 meter mark, and then find out the difference between the two, because the difference is the area that you're concerned about. Okay, and we have to do the same thing over here as well. We're going to find out the area from here and beyond. Okay, because remember, we can't, the value for the force of attraction doesn't increase as we get closer and closer to the center of the Earth. In fact, it will decrease. All right, so our calculations always start off from a reference of RE, the radius of the Earth. All right, so we always have to solve this from an evaluative point of view. Okay, so even though this work is the work that's done from the center of the Earth and beyond, we usually deal with it evaluatively. So we'll start off writing it down as this, okay, as just the general integral of it, which we'll call it UG. Okay, and at some point we're going to find out the differences between the two. In other words, the true definition of work is the change in energy, or in this case over here, the change in potential gravitational energy. Okay, that will be a formula that will be given to you. Okay. Well, if we just take a look at just UG by itself, then that's just the state function. It's just telling you how much potential energy you have at that moment. And you'll notice that whenever you calculate it out, because our radiuses are positive and G, M, and M are all positive, you'll notice that your UG will always be a negative value. All right, and what that tells us is that we're always in debt to the gravitational attraction between us and the Earth. Okay, in order for us to break free from Earth's gravitational pull, well, then we need to put in more energy than what we are in debt with. Okay, so if we try to move as far away as possible to a point where we're at infinity, then you'll notice that the value of U will eventually approach to 0, right? Because the value of G is a finite number. I'll just write down F for finite. Mass is finite, and the two masses are finite. But if the R goes to infinity, well, any finite number divided by infinity will go to 0. Okay, and that's what this crazy looking picture here is trying to describe. Okay, that we're always in this gravitational well that will always be sucked back to the Earth, and it isn't until we reach infinity that we will be debt free, and we'll be broken from the bonds of our attraction towards the Earth. Okay, but that's just all speaking right now. Let's apply what we just learned over here mathematically, right, to a real life scenario. Okay, and what we're going to do is that we're going to calculate out how much work is required to take an object and lift it by 100 kilometers from the surface of the Earth. We're going to approach this from a grade 11 perspective, and we're going to repeat it again using the proper calculations from what we just learned right now, okay, from a grade 12 perspective. Because in grade 11, you're assuming that G is always at 9.81. That over here it's at 9.81, over here it's still at 9.81. Heck, even at 100 kilometers away, we're pretending that it's still at 9.81 newtons per kilogram, or meters per second squared. Right, but in real life, as you move further away from the surface of the Earth, it's kind of like magnets, right? When you're close together, they're very strong, but when you move them further and further apart, the magnetic field attraction decreases quite a bit. All right, and the same thing happens with gravity as well. Okay, so let's start off from the grade 11 perspective. From grade 11, you might have learned that work is equal to mg delta h. Okay, so we have a mass of 1,000 kilograms. G will just assume that it's fixed at 9.81, no matter how far away you are from the surface of the Earth. And the height difference here, just be careful, 100 kilometers is equal to 100,000 meters. So watch out for that, right? Always stick with something known as MKS. It's a memory aid to remind us that distance is measured in meters, K for kg, right? The mass is measured in kilograms, and time is measured in seconds. Always convert over to MKS units before you continue calculating. Otherwise, your values will be off by 1,000. Okay, so you sub everything in. I'm just going to cut to the chase. You'll get an answer of that. Okay, good. You have a number. Now let's try solving this using the grade 12 approach, right? Where we know that the function looks like this, and we're trying to evaluate it between these 2 points over here. We have an R2 here, and we have an R1 over here. Okay? And work is the area underneath this curve over here. So since work by definition is the change in your gravitational state, then really it's just W is equal to UG in state 2 minus UG in state number 1. Where state number 1 is when you are at the surface of the Earth, and state number 2 is when you are much further away. Okay. The way how this calculation really works out is that you are calculating everything from the entire area, subtracting out the calculation from the smaller area. That's all you're doing over here. Okay, the big area up to here, so all of that, subtract the smaller area up to here. All right, and that difference will tell you the definition of what work is. That's all you're doing. Okay. Okay, let me erase all this stuff out because I know that I have it all PowerPointed out. Okay, work by definition, oh, I should have written U. Okay, work by definition is a change in your gravitational state. Okay. So UG2 subtract UG1. Things to keep in mind is that your radius is always a radius from the center of the Earth. All right, so your R1 would be from relative to the surface of the Earth, and the radius of the Earth is at about 6.4 is it kilometers? Yeah, 6,400 kilometers. All right, so you have to use that for your R1. Now, as for your R2, you have to add another 100 kilometers on top. Again, don't forget to convert into standard MKS units. Okay, so 100 kilometers is the same thing as 1 times 10 to the 5 meters. Right. So you have your R1, you have your R2. You can start subbing things in at this point over here, but if you try doing that in your calculator, you'll probably make a mistake somewhere. All right, there's just too much stuff to do at once. So why not just use a grade 9 hack? instead of subbing and all these crazy huge numbers in over and over again, why not just factor out first and then start solving? All right, so let's go through that. All right, we know that we need to type in 6.67 times 10 to the negative 11 twice in our calculator. Well, instead of doing it twice, why not just factor it outside of the brackets? Same thing with regards to the mass of the planet and the mass of the satellite. Instead of typing it out twice, why not just factor it out on the outside, and then whatever that's left inside the brackets, we'll let that be. Okay, so the first term that we have left is negative 1 over r2, and the second term is double negative, or plus 1 over r1. Okay, and this is correct. This is a good way to do it. Now, to clean things up, because usually this is hard on the eyes, we usually have the negative term placed afterwards and the positive term placed in front. So we end up getting r1 subtract r2. And with enough practice, you'll just end up doing this in your head anyway. So you just naturally know that when you rearrange it, it's going to look like this. Okay. No, this formula here will not be given to you on a test. You'll have to derive it out yourself. Okay. All right. So now that it's all cleaned up like that, it's a whole lot easier to sub everything in and calculate it out. How about you pause the video and try it out? Did you get to the answer of that? Good. All right. So yeah, these are just blatant numbers, but I just wanted to emphasize something. All right. The Earth, the radius is huge. Okay, that's what is the number over here? 6380 kilometers. Right, and you're just trying to move it just by a smidget more, just by another 100 kilometers. Okay, don't expect the value of 9.81 to dip too much. It's going to drop down to something, and if you want to calculate it out, then yeah, you could. G is equal to capital G M over R. All right, whoops, capital M. If you remember, if you recall that back in grade 11, okay, where the new R is the 6.48, and if you sub that in, you'll get the new value of G. Okay, when you're at the surface of the Earth, it'll be at 9.81. But when you're at 100 kilometers away, it's going to be some number that's slightly less. Okay. Now, because the differences here aren't too huge, these two values aren't too far different, right? 9.81 versus 9.65. If you calculate it as a percentage difference between the two, it's roughly 2% in difference between each other. All right. So the point is that if you can try it out for 10 kilometers, all right, if you're only moving it from the surface of the Earth to about 10 kilometers from the surface of the Earth, which is what you do if you're trying to fly in an airplane, the value of G doesn't change by too much, so you could probably get away with using this lazy calculation and figuring out how much work it takes to lift an airplane from ground all the way up to about 10 kilometers above the surface of the Earth, right? Whether if you do it the lazy way or the accurate way, you're going to have roughly the same answer, right? But when you're pushing 100 kilometers, then yeah, you'll have a 2% error. Now, 2% isn't too bad, because if you think about it, you're just simply taking a ruler and snipping off about this much from it. To the naked eye, you and I won't notice the difference. To an electronic device or measuring device, if it's calibrated properly, you'll notice it, but to the human perception, we're not going to notice something like that. Okay, so it's not too big of a deal. In fact, usually when we do calculations, we always want to buffer an extra 10% anyways, right? Like, for example, if you decide to replace the flooring in your bedroom, they'll tell you, IKEA, whatever square footage it is in your bedroom, add another 10% more, all right? Because if you make a mistake, at least you have the extra wood there. Okay, so 2% isn't that big of a deal. Now, what is a rather big deal is this case over here. Let's say that I decide to start from the surface of the Earth and now move 1,000 kilometers away from the surface of the Earth. Rinse and repeat from the grade 11 calculation and from a grade 12 calculation. I mean, if you want to pause the video and calculate it out, by all means. And if you did, good for you. That's great practice. And hopefully you got this answer here. Okay, and now when you take a look at it, these numbers do vary by quite a bit. In fact, their deviation is about 16%. Now it starts to matter. Okay, and here's another example. Again, you don't need to copy it. It's just to show you how bad it can get. Okay, so let's say that now you start from the surface of the Earth and now you move 2,000 kilometers away from the surface of the Earth. Not necessarily double of RE yet, or double the radius of the Earth, but you're just increasing it by a bit more, and you'll notice that your error now is quite significant. Okay, so yes, when you're near the surface of the Earth, and by definition of near, it's all arbitrary, but I'd say around 10 kilometers, then yeah, stick with the lazy grade 11 method. It'll give you a reliable answer. Okay, but if you are trying to move it at significant distances, then you can't be lazy anymore. All right, you have to go and do it the long way to get an accurate answer. Okay, because remember, as you move further from the surface of the Earth, the less attraction you have to the Earth, so the less work you need to do, right, in moving it further away. Okay, so the values will change, and that's why you'll see that the value does decrease over here. It takes less work to move it further away than it does for it to move. It takes less work to move something that's further away by a meter than it does require to move the object from a meter from the surface. Okay, so meter out there is a lot less work than over here. After all, when you look at the curve looks like this. Okay, for your force distance or your force radius graph between object and Earth. I think that's it for the first part. All right, so that's on gravitational potential energy. The second part of today's lesson is on escape speed. Oh, one more example. Why not? Go through this. Okay. All right. Hopefully you've unpaused and you want to see the answer. Okay. What is the force of attraction between the moon and the Earth? You're looking for your Fg. And what is the moon's gravitational potential energy relative to the Earth? You're looking for Ug. So when you sit down and you calculate it out, those are the answers that you should get. Good. Okay, now on to the second part. Sorry about that. Okay, escape speed. All right. Now, when I take an object, which I dropped on the ground already, well, I'll just take this object over here. If I put in a little bit of effort and it's moving at slow speed, yeah, it'll come back to me. If I put in more effort, yeah, it'll still come back to me. If I whip this really hard, at some point it will come back to my hands again. All right. But if I whip it super, super hard, I can break off the bonds of gravitational attraction, and the amount of kinetic energy this will have will exceed the amount of debt that I have between the relationship of this and the Earth, and then it'll move away from Earth indefinitely. And that's what escape speed is. Okay, so escape speed can be accomplished if you have more kinetic energy than you have of this gravitational potential energy. So by definition, the total energy that's in an object is all the kinetic energy plus all the potential energy. Okay, plus all the internal energy if you want to be all technical about it, but we're not dealing with internal energy today. Okay, so kinetic energy, gravitational potential energy, and we want to ensure that this is greater than 0. That's how we can find out what escape speed is. Okay, so by definition, that's what escape speed is. Ek plus Ug is greater than 0 joules. You can derive an equation with this now. Okay, now if we bring Ug over to the other side, yeah, it'll become negative Ug. Not that big of a deal. Kinetic energy, if you recall from grade 11, is 1/2 mv squared. Ug that we just learned right now is equal to negative g m little m all over r. Yep, the double negatives become positive. What is also true is that little m is the little object. Okay, if you bring the 2 over, you get that. And lastly, if you square root both sides, you end up getting that. And that is the official equation. There you go. The escape speed, or some people might write down as escape velocity, is equal to this formula over here. Do I have an animation? I can't remember. Oh yeah, I do have a cute little animation. Okay, so I've done the calculations already. If you have the object travel any less than, what's the magical number? That, okay, less than 11 kilometers per second, then yeah, the object eventually will come back to Earth. All right. Now in this case over here, you'll notice that I launched the object, I guess, level to the Earth. All right. But you could also launch it vertically. It doesn't matter. Why doesn't it matter? Because this is a scalar quantity. Remember that energy is scalar. Direction doesn't matter. You can throw in any direction you want. If it's less than this numerical value over here, unfortunately, this little guy will just keep on orbiting around. All right. And yes, it will speed up as it gets closer to the surface of the Earth, and it will slow down as it moves further away. Conservation of momentum. We covered that last unit, didn't we? Yeah, we did. Okay. All right, but if you exceed that value, then yes, the object will never come back again. Okay, this picture over here, why did I post this? It's from that simulation from the previous video after you've watched it. Hope you did. All right, and this is just emphasizing that if you don't put enough kinetic energy, it'll just come back to the surface of the Earth. If you put just enough for it to orbit, that's nice and dandy, but as you apply more and more energy, it'll just orbit. It'll just look more egg-shaped. You need to exceed the amount of debt that you have in potential gravitational energy for it to be like example, I think B. I don't even know what it is, but you have to travel fast enough that it will just never come back again. Okay, and that's what escape speed is. Okay, so for the final question of today, all right, you have an object, you launch it from the Earth, and when it reaches 1,000 kilometers, it's still traveling at 6 kilometers per second. Part A, will it break free from the Earth's gravitational bond? And B, if it doesn't, how far away from Earth will it be before it eventually comes back down? Okay, so for part A, what we're trying to calculate out is the total kinetic energy that it has plus the UG that it has, is it greater than 0 joules? Okay, if it is, then yes, it'll break free. If it doesn't, it won't. Okay. Things to keep in mind is that even though this is 1,000 kilometers above Earth's surface, all our calculations must be measured from the center of the Earth. Okay, so this 1,000 kilometers is somewhere out here. So we need to first factor in that the radius of the Earth is equal to 6.38 times 10 to the 6, and we need to add another 1 times 10 to the 6 to it. All right. So technically, our r over here is equal to 7.38 times 10 to the 6 meters. Keep that in mind in your calculations. Did you get the answer? Unfortunately, you don't. Okay? Yeah, let's go through and calculate this out together. Why not? Okay. All right, we'll start off with our givens. We have our r is equal to re plus our, I'll call it delta h. Okay, so 6.38 times 10 to the 6 meters plus our 1 times 10 to the 6 meters for 1,000 kilometers. That will give you 7.38 times 10 to the 6 meters. What else do we know? We have our mass, which is 1,000 kilograms. We have our big mass, which is equal to 5.98 times 10 to the 24 kilograms. Don't worry, that's a constant that I'll give to you as well. Oh, it's up there on top. Good, I memorize these numbers. Memorizing is good. Speeds things up. Same as g. G is equal to 6.67 times 10 to the negative 11 newtons times meters squared all over kilograms squared. All right, so we can go off and calculate this out now. Okay, what is the total energy that this thing has? 1/2 of the mass of the 1,000 kilogram satellite, I guess, or rocket, multiplied by the speed that it's traveling at. 6,000 kilometers per second is, 6 kilometers per second is 6,000 meters per second. Remember to convert to MKS units. Okay, I'm going to add it with negative 6.38 times 10 to the, 6.67 times 10 to the negative 11 newtons times meters squared over kilograms squared, multiplied by 5.98 times 10 to the 24. I'm going to run out of space, so unfortunately I'm going to drop the units, but make sure you include the units when you're subbing it all in, times 1,000, all divided by r. And again, that's the final radius of 7.38 times 10 to the 6 meters. Crunch that through, and you should end up with a negative answer, okay, of negative 3.6 times 10 to the 10 joules. Meaning that you still need another 3.6 times 10 to the 10 joules of energy at that point for it to break free. And you can calculate out the equivalent speed from that if you wanted to, right? Ek is equal to 1/2 mv squared, so you can solve for that v. Okay, what additional speed is really needed? Okay, and part B, well, since it didn't make it, well, then what's the maximum height above the Earth will it reach before it falls? Okay, all right, to solve for this part over here, well, we have to keep in mind the conservation of energy, all right, where the total kinetic energy of at the beginning plus the total gravitational potential energy of the beginning is equal to the total kinetic energy of at the end plus the total potential energy you have at the end, okay? EKI, UGI, EKF, UGF. Okay, yeah, we couldn't use the formula from back in grade 11 because at 1,000 kilometers, as we done the calculations earlier, you'll have a 16% error. All right, so you can't use any shortcuts. You kind of have to do it the long way here. Okay, so what can we do with this formula here? Well, we'll call this EKI of this initial state over here. Okay, so it's the state that it is when it is already at 1,000 kilometers above Earth's surface. Okay, so our EKI will be based upon our 6 kilometers per second, and at maximum height, your EKF goes to 0. All right, at maximum height, things pause before they come back again. All right, so to find out the maximum height, we need to figure out the value of R for your UGF. Okay, so now that we have the formula written out like this, it's up to you how you decide to solve it from here and beyond. Okay, with that formula there, I think I have it all PowerPointed out. Yes, I do. Okay, so I'll explain this through the PowerPointed example. Okay, so yeah, you replace your EKI with these formulas as well as UG, and then you slowly isolate for your RF. Okay, keeping in mind that your initial height is the radius of the Earth plus whatever initial height that you're at. Okay, plus 1,000 kilometers. Same as your HF. What height will it be above the Earth? Well, some people will just subtract RE at the end, or you can write it down as an equation like this, which will automatically subtract for you, and you'll see what I mean when you solve it this way. Okay. All right, so you have it rearranged like this, and we want to slowly isolate for delta HF. So first thing we're probably going to do is we're going to divide every term by negative GMM, right? So that will disappear off over here, that'll disappear off here, and then we can bring it down as a denominator for the first term, and it'll look like that. Another thing that you'll notice is that every term over here has little m, so the little m's all divide each other out. Okay, so that's how it looks like this. Next, what we want to do is, well, I guess you could do the reciprocal of this if you wanted to. Is that what I did next? Yeah, I did. Okay, I did the reciprocal of that. I just rearranged, did the reciprocal, so that RE plus HF is equal to the reciprocal of that, and we brought the RE over to the other side, and that's what I mean. Mathematically, it's going to automatically subtract that for you. Okay, sub everything in super carefully, and then you'll get to your answer. Okay, of 4,700 kilometers above the Earth. That's as high as it's going to get if it's already traveling at 6 kilometers per second at 1,000 kilometers above the Earth's surface. Okay, so yeah, there are other challenging examples like that in your homework tonight. And if you want to look at the answer key, well, here we go. Here's the answer key for 4, answer key for 5, answer key for 6, and answer key for number 7. Oh, a few more, 8 and 9, and I believe 10 and 11. So best of luck in your homework, and I'll catch you in the next episode.